Okay, so it's just about time, but I'm going to just wait a couple of minutes and see if some extra people turn up as well. We're still doing intro to stats. I think it's week 10. I hope it's week 10. And we're going to do some of the questions off the exercise sheet. I think I'm going to do question 2, question 4 and question 5 if we get time. The reason for this is that question 1 kind of guides you through quite well what you need to be doing anyway. Question 4 is very similar to, and question 3 is revision because it's about biased and unbiased estimators. So we're going to skip over number 1 and 3 and focus instead on number 2, number 4, and if we get time, number 5 as well. And we've just got extra people joining us, so I'm going to wait another couple of minutes and see if we get up to around about 20 people, which has been the number of people who typically attend. Yeah, afternoon, everybody. I'm going to wait one more minute and just see if anybody else turns up. There's 18 of us at the moment. Typically there's low 20s, but might well be that, you know, we get into the crunch end of the semester and, you know, people would rather watch the recording, and that's not a big deal. So I'm going to repeat myself for anybody who's just joined us. We're going to try and do question 2, question 4, and maybe question 5 if we get time. These are questions on hypothesis testing and confidence intervals. Question 1, I felt we could skip over because it's kind of, it guides you through quite well. It's fairly easy to follow what you need to do for question 1. And question 3 is really a topic that we've covered already. It's about biased and unbiased estimators. So I'm going to leave those 2 and instead jump straight in with number 2 and then move on to number 4, and if I've got time, number 5 as well. As always, there's going to be some gaps for you to try and give things a go yourself or check the answers that you've already got if you've had a chance to look at this sheet already. If you've not had a chance to look at the sheet, as I always say, it might be that I don't give you enough time. That's in order to try and show you as much of the solutions as possible. So let me just switch to the visualizer and we will take a look at question 2. It's also really, really cold today, I have to say. So if you're in the UK and you're freezing, not like me, make sure you've got enough extra layers on because it's so cold. Okay, so question number 2. Question number 2 was about light bulbs now. I'm not really too sure why hypothesis testing questions always have to be about light bulbs, but you know, we need to go super trad for this one. We've also got all of the values in a paragraph of text rather than like laid out for us. So the first thing we want to be doing is thinking about for each data set what the key statistics are that we've been given. So we know that for the first batch, we had 150 items, and we had the mean value of that sample, of sample A, as 1386, and the standard deviation of sample A of 114. And for sample B, we had 200 observations, a mean of 1218 of the second sample, and a standard deviation of the second sample of 98. Now, we weren't given any additional assumptions about the underlying data being normal. So we can't make any kind of assumptions about the underlying data being normal. But so it's not mentioned that we can assume that the underlying data is normal. So, you know, we've explicitly got to not assume that. Often with these, or rather with these types of questions, often it's a case of really struggling to, you know, decide what assumptions apply so that you know which formula you want to be using. And the formulas are very similar to, and we really need to be able to pick out you know, what's going on in each particular case. So you're going to have a different formula for normal, if you can assume that the underlying data is normal and non-normal. So let's make that explicit. In both cases, we've been told we don't know what the variance of the underlying distribution is. We've been told in the first part that we're pretty sure that that the underlying variances are not the same. So the samples have different variance. The samples are taken from a population populations which don't have the same variance. And then in the second part, we come to where we think that the variances are the same. So in the first part, we're going to focus on the case where we don't, we think the variances of the underlying information are not the same. Okay. And we're interested in a 95% confidence interval for the difference between the two means. So we're interested in 95% confidence interval for the mean of A and the mean of B. So, and those are the population properties, not the observed quantities. So we've observed these two means, and we want to say, well, what kind of range do we think the difference between the means of the underlying data, or you know, the means of the distributions that we're not too sure about should be. Okay. So the first thing I'm going to do is I'm going to remind myself that with a confidence interval, and this is what's left over here. So it's going to be 0.05. And in this case, because I'm not allowed to assume that the underlying data is normal, I'm going to be using in my formula this value Z1 minus alpha divided by 2, which has cropped up an awful lot before. And if I use this value of alpha, it's in this case, it's Z 0.975. Now, what this is this is the value that when I plug it into the CDF of the normal distribution, this one gives me as an output 0.975. And I can look up what Z will satisfy this equation in the normal distribution table. And I find that it's 1.96. So that's a really useful fact for carrying on with this question. So with that in mind, I want to be looking at what the endpoints of this confidence interval are. So I want to be centering my 95% confidence interval on the thing that I know, which is the difference between the two means that I observed from the samples that I've taken. Okay. And then I've got a plus or a minus because I'm going to want to go slightly to the left and slightly to the right for each end of the confidence interval. And then I'm going to be using Z, the relevant Z, so Z.975. And then I've got something that needs to go in a square that I need to take the square root of. And in this case, because I don't know, because I'm not allowed to assume that the information is coming from two distributions with the same variance, I can actually just use the observed standard deviations. So the standard deviation of A squared divided by the number of elements in A, and standard deviation of B squared divided by NB. Okay. So these are going to be the endpoints of the confidence interval in question. So you should now be able to calculate that because you should be able to plug in all of the values that you were given in the question, so these ones, into this equation and get a 95% confidence interval. So I'll give you maybe a couple of minutes to plug in all of those values and check that your answer, if you've had a look at this question in advance, is the same. If not, to just give it a go and calculate. Yeah, so give a go of finding the right values, plugging them in, deciding what the end confidence interval is. I'm going to give you like maybe 2 minutes, and then we'll move on to what we're going to have to change if sigma squared A is not equal to sigma squared B. So if you've already done this and you're confident in your answer, have a think about what you would need to be changing if we were assuming that these two are the same. Yes. Okay, so that sounds like this is actually a week 10 of Intro to Stats featuring my family. but never mind. So if we take the values that we've been given in the question, plug them into this formula, we should get the endpoints of the confidence interval of the form 1.68 plus or minus 1.96 times the square root of 134.66, this one. And that means that my confidence interval is going to look like 145.29 to 190.74. So what is this telling me? It's telling me that I am 95% confident that the difference between the means, mu1 and mu2, is between these two values. So we're pretty sure that there's quite a substantial difference between these two values of the mean. Okay. So let's have a look at how that's going to change if I'm allowed to assume that the underlying distributions have the same variance. So the underlying distribution of A has variance sigma A squared, and that's exactly the same as the other one. Now, the first thing we want to be doing is we want to be thinking about what an estimator for the joint, what a good estimator for the joint variance should be. So I'm going to call this joint value sigma squared because it's the same regardless of whether we're looking at sample A or sample B. We're assuming that they've got the same variance. And a good estimator for the joint variance Yeah, so Elka there is telling you exactly what she thinks about statistics. She's not impressed. Never mind. Okay. So joint variance can be estimated by, so I'm going to have sigma hat squared, and I'm going to set this equal to, I'm going to say NA minus 1 times the variance I observe from sample A. And n minus b, so nb minus 1, and then the variance I observed from sample B, and then I'm going to divide by the sum na plus nb minus 2. Okay. So that sort of makes sense if you think about what the formula for the variance of each of the samples is, because we divide in each case by 1 minus NA. So 1 minus the number of elements in the sample in order to get an unbiased estimator of the variance in that particular sample. So the multiplying by NA minus 1 and NB minus 1 kind of remove those factors. And then here, what I'm actually dividing by is NA plus NB minus 2, because it's two separate samples I'm looking at, the degrees of freedom needs to be reduced by 2 in order to make it an unbiased estimator. Okay, so there we go. Okay, so I'm going to use this as an estimate for the joint variance. And then how is that going to impact the endpoints of the 95th% confidence interval? So that's going to change in some way the formula that I want to be using for the endpoints of the confidence interval. And I want to give you a moment really to kind of have a think about what you would want to be removing from that expression. And what you might be wanting to replace it with. You can check your notes, check any examples that Sarah Lees has given you, and maybe try and crunch out the confidence interval again. And I'll give you a little bit longer this time, I think, like maybe a solid 3-4 minutes to think about what you'd like to change, calculate the value, and then we'll go through together to make sure that we're in the same kind of ballpark with the second part of this question. So Kamal says SA equals SB this time. So fairly close, Kamal. So certainly the values that I'm going to want to be putting in here are not going to be different for the two samples, because I've assumed that that they should have the same underlying variance. So I certainly want to be taking out the SA and the SB out of here. So it might well be that, you know, even if I had two samples from the same distribution, it might just by chance be that, you know, that the variances, that the standard deviations that I found from those two samples would be quite different. So here, rather than just put in two separate values which by chance are different, I want to be putting in sort of a better estimate for what I might think that the variances should look like. So yeah, give that a go. Might be something to do with this guy, you know, might be something to do with this guy. Oh. Okay, so apologies for leaving outside if you're just the person who's just joined us. I'm very sorry about that. We're taking a look at the second part of question 2. The question I've posed is, what do I want to do to the endpoints of the confidence interval that I was using in part A? So what do I want to do to this term here? If I think that the standard the data in sample A and sample B is picked from two distributions which have the same variance in each case. Now I felt a little bit like I'm rambling a little bit and talking over you know, the time that you've got to calculate. So I'm going to say that, you know, Kamal was definitely barking up the right tree with saying SA equals SB this time. Well, it doesn't necessarily, because they're two separate samples, so we could have observed different values, but we want to be, rather than using SA and SB, using the same joint variance estimator for each one. So the first thing you needed to do is to stick the numbers for NA and SA and NB and SB into this formula, which would hopefully have given you 11,056.32. And then here we've still got 0.196 because it's still a 95% confidence interval, but what we want to be putting under the square root term is going to be, first of all, the estimator for the joint variance, this one, and then I'm going to be multiplying that by 1 divided by NA plus 1 divided by NB. Okay, if I used the values given to me in the question, I'd end up with 168 plus or minus 1.96 times square root of 128.99. which means that my 95% confidence interval is 145.74 and then 190.26. So you can see this one is really, really similar to the one that we got with without assuming that the variances in the underlying distributions were the same. This one's just very, very slightly bigger, very, very slightly bigger. In both cases, 0 isn't in these confidence intervals. So we can be pretty certain that that mu A doesn't equal to mu B. So we can't say for sure that they're definitely not equal, but we can be pretty certain if it's not in the 95% confidence interval that that it would be a push for us to assume that that the means are the same. Okay. So question 4 initially feels like it's really, really similar because rather than light bulbs, we've been given headache medicines, but we've again been given 2 samples, sample 1 and sample 2, from 2 different brands. But we've been told that we can assume that that the means are normally distributed, that the underlying data is normally distributed. Okay. So specifically it says, assume the absorption times for the 2 brands are normally distributed with a common but unknown value of sigma squared. And we don't know what sigma squared A or sigma squared B are, from the 2 different brands, but we know that we can be fairly confident that they are the same. So the question asks us something really similar to question 2. It asks us to find a 95% confidence interval for the difference between the 2 means. Ask us to find 95% confidence interval for mu A minus mu B. And it's set out the data for us in a table in the question. So at first glance, I'd be saying, okay, so this is very similar to this previous one. It's very similar to this one. So what has changed is this assumption that we can assume normally distributed underlying data. So something in here is going to change. What is going to change if we're allowed to make that assumption of normality? So I'd like you to take a little look at that. Have a think about what you think is going to change and see if you can calculate the confidence interval. Because we're assuming that the 2 variances are the same, we're going to be wanting to look for an estimator of the joint variance again. And just as a little hint, I'll give you the mu hat squared. So the estimator for the joint variance in this case is 64. So 65.97. Okay. So again, I'd like to give you like just a few moments to have a think about that, maybe 3, 4, 5 minutes, something like that. Have a think about what you're going to want to change. Have a think about where you're going to find the thing that you need to change. If you face a challenge finding what you need, tell me what the problem is in the chat. Somebody in one of the previous classes pointed out to me that there is a little bit of a challenge there. So if you run into a little difficulty that you're not too sure how to fix it, let me know. And we'll come back in a few minutes to run through what formula you should be using and how to get the competence interval in question. Well, certainly what was going under the square root here was exactly the same as in the case then. I couldn't assume a normal distribution. So it would be the estimator for the joint variance and 1 minus. So 1 divided by NA plus 1 divided by NB. And then something would go here. And then because we're allowed to assume the normally distributed underlying data, this is not going to be from, it's not going to be a Z anymore. It's going to be T. And this is a value from the student T distribution. With degrees of freedom equal to the number of points observed in total. So I had 12 elements in both samples and -2. Now, the difficulty that I was informed of in the previous class was that the table that you've been given for the student T distribution doesn't have 22 degrees of freedom as a row in it. So what do you do? What do you do if you've only got the rows that have 20 degrees of freedom and 24 degrees of freedom? And what you need to be doing is you need to be looking at the closest Y22, because we've got 12 elements in our first sample, 12 elements in our second sample, and we're losing 1 degree of freedom for each sample that we've got. So we've got 24 observations in total minus 2 because of the loss of the 2 degrees of freedom. So that's Y22. And then when you come to the table, I want you to look at the row, the 20 row. And the reason why you look at the 20 row is because if your table doesn't have the row in that you need, so it doesn't have 22 degrees of freedom, apparently in the table that you guys have been given, you look at the one that's nearest but lower than. So you look at 20 and then you find the value in the row for 20 if that's all you've got. Okay. So if you look that up, you find that that number is 2.74. Okay. So again, you put all of your numbers together and you will find that you end up with a confidence interval that looks like that. So minus 3.98, 9.78. Now, again, we can't be 100% sure about whether the means of these underlying data from each sample is the same, but we can't discount it as a possibility because 0 is in the 95% confidence interval. We can't rule out that the hypothesis that the means are the same. So can't rule out the possibility that mu A is equal to mu B. So we've got a few minutes to look at question 5, which is fantastic because I went a bit too slow on Tuesday and didn't get a chance. So question 5 is a little bit different because we've been asked to compare the ratios. So we've been told that we've got we've got some numbers of registered voters in two different areas. And then we've got a number of active voters, so number of them that actually vote. We've got the proportion that actually turn out. So in the first case, so in area 1, we've got 288, and in area 2, 216. I'm going to call these ones R. In terms of active voters, 1441 and 125. So our estimate for the proportion of voters that are voting in area 1 is going to be 141 divided by 288. And the estimate for the proportion of voters voting in area 2 is going to be 125 divided by 216. So in this case, 0.4896. In this case, 0.5787. Now, what we've been asked to do is to find a confidence interval for the difference between these proportions. So
We obviously don't know exactly what proportion of people vote in the two areas. We've only got our subsamples to observe. And from these, we want to come up with a 95% confidence interval for the difference between the actual proportions in the two areas. Now, this is a little bit tricky. It's a little bit tricky and it's a little bit different than question 4 and question 5. Because whether or not the voter is active is going to be binomially distributed, because we're going to have a certain number of people in the population at large and a certain proportion of them are active or not. So we're going to want to incorporate in there in some way the standard error. Of PI. Which is equal to PI minus 1 minus PI, which is definitely a kind of an estimate for the variance of the number of people in the sample that are actively voting. So we're going to want to include the standard error of PI somewhere in our confidence interval. So maybe if I give you the formula and then we'll take the final few minutes of the tutorial for you to plug in the values and see what you get. So I'm going to want to be centering my confidence interval around the difference between the observed ratios and then plus or minus, because again, well, I know that this data is not normally distributed. Oh, it's not been specified. I get to put Z here, which is nice because I know what the value of Z 0.975 is by this point. It's been burned into my brain as 1.96. And then the square root. And I want to put the standard error divided by the number of observations in the first sample and the same with the second one. Standard error from the second sample. Number of observations in the second sample. Okay. And I should be able to just grab all of the values from the question and plug those in and get my 95% confidence interval. And I just wanted to give you a chance to do that. And then to, based on the values that you get, draw a conclusion. So do you think that the same percentage of people, or the same proportion of people in the two different areas are going to turn out to vote? So Kamal says, yes, he thinks that the same proportion of them are going to turn out to vote in the same, in each area. So I'm assuming that when you found the end values of this confidence interval, Kamal, that 0 is in the confidence interval that you found. Is that right?
Okay, so Yeah, so my question is when you plug the values into this, so that you've got a confidence interval, so that you actually know what the confidence interval is, the lower number here is negative and the bigger number here is positive. So 0 is in that range somewhere. Is that right in your case, or have you got both negative or both positive? Yeah, I also got both negative. One of them is really, really small, so it is very, very close to 0. Yeah, I can sort of understand, that if maybe if you made a calculation error, you might get one that was so close to 0 that it would give you the impression that you can't rule out the possibility that the difference is 0. But I got 2 negative values. I got minus 0.77 and minus 0.0015. Now, I've got 95% confidence that the actual difference between P1 and P2 is in this range. So sadly, I can rule out the possibility that P1 equals P2. So, and the reason why it's plausible for me to assume that they're not equal is because 0 is not in the confidence interval. So this is something that is really quite tricky in terms of the conclusions that you're drawing, because you can't say for certain one way or the other. It's not a definitive yes or no, because you might have just observed some really, really strange or unusual or unlikely data in one of your samples. But we can be reasonably sure that these 2 sets of data were picked from populations which have different properties, because 0 isn't in the confidence interval in question. Okay, so I've run over by 3 minutes. I'm sorry I've run over by 3 minutes. I hope those 3 minutes were useful to everybody. And I'll see you next week for more hypothesis testing. Okay, so yeah, feel free to leave whenever you're ready. Have something if you want to. We've got about 12 minutes before I'm going to do it all over again. All right, bye-bye, everybody. Okay, so welcome to the new people who are very early, or no, not very early, but 10 minutes early for the next class. We're gonna hang around and just kind of chill a little bit while we wait for everybody else to turn up. If you want to chat to each other, feel free, of course. I wouldn't know if you were doing so. So you're more than welcome. If you want to ask any specific questions, I'll be around. You can do that. And if not, just relax and we'll get right on with it pretty soon when some more people have turned up.
No, I need to write something.
Okay, hello everybody, and welcome. It's Intro to Statistics, week 10. Lots of stuff on hypothesis testing and confidence intervals. Fun. I'm gonna wait just like maybe a couple more minutes to just see if anybody else turns up before we get started. The goal is to attempt to do question 2, question 4 and question 5 if we get time. I've chosen to do these ones for the following reasons. Question 1 is quite straightforward and guides you through what you need to do. Hopefully you've all had a chance to take a look at question 1. So we're going to skip over that one. Question 3 is about biased and unbiased estimators. So it covers a topic that we've spoken about a lot in the past. So we're also going to jump over that one. Now, the idea of approaching question 2 and question 4 is that they are really kind of similar, but they kind of show how the assumptions that we're making, how we need to change the confidence intervals we're looking at. And question 5, again, I picked that one because it's kind of similar again, but different in its own special way. I think it's interesting for us to know what you need to do in the case of 5. So yeah, we got one more person that I'm going to let in, and then I'll switch over to the visualizer and talking you through what we're doing. As always, there's going to be some little gaps for you to either check your calculations or to have a little think about what we need to do next. You can take that opportunity to look up in your notes what you think we should be doing, checking what you've done, or just generally kind of thinking about the questions. They might go a little bit too fast if you've not had any opportunity at all to look at the sheet in advance. But I really hope you have. Don't worry if you haven't, there's always the chance to look at it before your exams. It's coming up though. Okay. Let's go. Okay, so the first question we're going to look at is question number 2. And question number 2 was about light bulbs. So it's like a super traditional question when it comes to hypothesis testing. And we were given in the first paragraph lots of information. We were told we've got two distinct samples with different means and different standard deviations. We weren't given any other assumptions whatsoever. And then we were told if the data is coming from 2 underlying distributions with different variances or the same variance, what range do we think that the difference between the means is going to be? So so we were given in the question the number of observations in each sample, 150 and 200 observations, the means in each sample, so X bar A and X bar B. And also the standard deviations in each sample, so 1, 14 and 98. Okay. we're not allowed to assume that the underlying data is normal because we weren't told anything explicitly about that. And what we were asked to find is 95% confidence interval for mu A minus mu B. So the difference between the actual means from the two distributions. We don't know what either mu A or mu B actually is. We've only got a sample that we're observing in each case. And we want to have a confidence interval for what that difference could possibly be. And in part, the first part, we were asked to assume that sigma squared A is not equal to sigma squared B. So we assume that the variances from the underlying distributions are different. So in this case, because we're looking at the 95th% confidence interval, I set alpha equal to 0.05. Something that's going to be used in my confidence interval is the value of Z1 minus alpha divided by 2, which in this case is Z 0.975. Now, what is this Z creature? It's a value so that when I put it into the CDF of the normal distribution, so I put Z.975 in there, the value I get out is 0.975. So Z solves this equation, and hence I can use my table to look it up, and it's 1.96. And we're going to see a lot of 1.96 in this tutorial. It's our new best friend. Okay, so the confidence interval that I'm looking for has endpoints given by the following equation. So first of all, x bar A minus x bar B. So I want the middle of the confidence interval to be the difference between the two sample means, and then plus or minus. And then what I'm going to be putting here is Z 0.975, and then something in a square root bracket, square root here. So I'm going to be putting in SA squared, so my estimate for the variance from the first sample divided by the number of elements in the first sample, and then add on to that the same for the second one. So my unbiased estimate of the variance of the second sample divided by NB, the number of elements in the second sample. Okay. So great. We've got ourselves a formula. Hopefully we're fine to take all of the values there, chuck them into this confidence interval, and get a value of the confidence interval out. So I'm going to give you literally just a minute or two to double check your answer for this one. So double check that you're using the correct formula here, and stick the numbers in that we've been given to get the two ends of the confidence interval. And I'll tell you in a couple of minutes what values I got, and we can double check whether we all got the right values. Okay, I've just let somebody else in, and I'm really, really sorry if I had left that person sat in the waiting room for more than 30 seconds or so. Yeah, I missed the fact that you were waiting. Apologies. So if I take the values I was given in the question, these ones, chuck them into my formula here. I'm going to have the endpoints of my confidence interval of the following four. 168 plus or minus 1.96, and then the square root of 134.66. Okay, and this is going to mean that the 95% confidence interval that I'm looking for is this. It's 145.26 and 190.74. So I can have 95% confidence. Now it's not 100% obviously, but I can be pretty damn confident that the difference between the means for the two samples, mu A and mu B, is between 145.26 and 190.74. So what's going on there is that I'm using this assumption, I'm pretty sure that the difference between those two means is moderately large, so between about 146 and 190. So, you know, I'm thinking maybe that those two underlying distributions don't have the same mean if I'm expecting the difference to be that big. Okay. So what do I need to change for the second part of the question? So for number 2, I've been told that do exactly the same thing, but in this case assume sigma squared A equals sigma squared B. So that the variances of the two underlying distributions are the same. So with this in mind, the first thing I'm going to want is an estimator for the joint variance. Now the idea here is that if I use the data from both samples in order to estimate the joint variance, I'm going to get a more accurate estimate than if I just use SA and SB to get individually. So my estimator for the joint variance is going to be sigma, I'm going to call it sigma hat squared. And I'm going to calculate this using NA minus 1 times SA squared plus NB minus 1 divided by SB squared. And then all of this needs to be divided by NA plus NB minus 2. Okay. So the idea here is if you think about the formula, the usual formula that you use for the unbiased estimator for the sample variance, so the usual formula you'd use for SA and SB, and that's a sum, and we divide that by 1 minus, we divide it by n minus 1 in each case, because by dividing by n minus 1, we get that unbiased property, whereas if we divide by n, we end up with a biased estimator. So that's where multiplying by the NA minus 1 and NB minus 1 comes from. It comes from undoing that standardization, that multiplicative factor in the usual formula. And here we divide by NA plus NB minus 2, because now that we've got 2 separate samples, we're losing 2 degrees of freedom overall in order to make an unbiased estimate. Okay. So with that in mind, what I'd like to give you 5 minutes to try is have a think about what you're going to want to change about this formula to incorporate the fact that we're now assuming that the 2 variances are the same, and recalculate what the endpoints of the 95% confidence interval are with this changed assumption. So the first thing you're going to need to do is calculate this one, come up with a formula similar to this one, but possibly a little bit different because of our different assumptions, and plug the values from the question into your new formula to find the 95% confidence interval. And we're going to come back at 20 minutes past 5 in order to run through together before we draw a final conclusion and then move on to question form. And as is usual for Thursday afternoons, I've been talking for too long with multiple classes back to back. So if you hear me slurping, it's in order to try and not lose my voice in the next 30 minutes. Okay, so let's have a look at what we want to be doing here. So hopefully as a first step you could get all of the values in here, and what we would get out as an estimator for the joint variance would be 11,056.32, this one. Okay, and then what we want to be doing is we want to be replacing the SA squared and the SB squared in here with our estimator for the joint variance, because we think this is going to be a better guess for what the joint variance should be than either of these two is going to be. So then the endpoints of the confidence interval. They're given by the formula x bar A minus x bar B, and then plus or minus, we're still going to have Z 0.975 in there, and we're still going to have a square root, but what's going to go in the square root is the value of the estimate for the joint variance that we've got, and then times by a factor of 1 divided by NA plus 1 divided by NB. Okay, if you crunch out what those values are, what we end up with is again 168 plus or minus 1.96 times by the square root of 128.99. This one. So in this case, the 95% confidence interval is 145.74 and 190.26. So you see that those are relatively similar between the two parts. Now, this one here is very, very slightly more narrow. So slightly less values in this one than there is in this one, but they are really very, very similar there. Now, in both cases, 0 isn't in either of those confidence intervals. Now, we can't say 100% guaranteed for sure that they're not from the same distribution. We would never be able to say with 100% certainty that they're not from the same distribution. But we can kind of rule out the possibility that they are if 0 is not in the 95% confidence interval. So 0 is not in the 95% confidence interval, implies we can plausibly assume that mu A does not equal mu B. Because it's reasonable for us to say that that difference shouldn't be 0 if the 95% confidence interval that we generate doesn't contain the value 0. Okay. So moving on to question 4. We were given a very similar kind of situation, but there was just one change between question 4 and the second part of question 2. First of all, we were given different underlying data, so the N's and the S's and the X bars were different, of course. In this case, we're looking at the effectiveness of a couple of different headache cures, and we were told that we can reasonably assume that the underlying data is normally distributed. So, in particular, what we were told was assume that the absorption times for the two brands are normally distributed with a common but unknown value of sigma squared. And we were told that we had 12 observations in each case of what the absorption times were. So we can assume normally distributed. And also sigma squared A equals sigma squared B. Okay, is what we've been told we're allowed to assume. So what's different there is that now we're allowed to assume normally distributed underlying data. So that's going to change something about the 95% confidence interval that I was calculating in question 2, part B.
It's going to change something about what goes in there. So what I'd like you to do is calculate the estimator for the joint variance. Calculate x bar hat, and think about what formula you want to use for the 95% confidence interval in this case. It's going to be a little bit similar to this one here, but there's something that we're going to have to change because we've assumed normally distributed underlying data. So I'm going to give you until past to have a think about that. So calculate the joint variance, have a think about what you want to change in this formula. If you feel confident about what you want to change it and do the calculation. If not, just wait until past. We'll come back, we'll decide what we need to change in this formula, and we'll move forward from there. Now, there is one very tricky little thing that's going on there, and we'll have a little chat about that. Somebody pointed that out to me in the Tuesday morning tutorial, but we'll come to that in a moment. I think it's only fair that I move that down a little bit for you so that you can see the formula for sigma squared hat, the sigma hat squared that I used before. Okay, so I hope that by plugging in the numbers for this question into this equation, you managed to get yourself to 65.97. And then also, when you were looking at this confidence interval and trying to decide what to change, I hope you were thinking well, I can't really do anything about the X bars. They should definitely be like that. They're always like that, regardless of what underlying assumptions they have. I hope you were thinking that maybe you should also leave the square bracket, so the square root alone, because again, we've got the situation where we assume that the two variances are the same, so we need a joint variance estimator. So we're definitely going to leave those bits the same. Now, what you need to change is this value here that goes outside the square root. And in this case, because we've assumed normally distributed, rather than having z, which is a value related to the CDF of the normal distribution, we have a value t, which is related to the student t distribution. Now the suffix is the same, it's still 0.975, but this value is from the student t distribution. Why 22? Now it's 22 because we've got 12 elements of each sample. NA is equal to 12 and B is equal to 12. And we've lost 2 degrees of freedom because we've got 2 separate different samples. So that's why we've got 22 degrees of freedom overall. Now the difficult thing is that you will struggle to find that value of T in the table that you've been given. Because your table only has 20 degrees of freedom and 24 degrees of freedom. So in that case, what do you do? And this was a really good question that somebody asked me in the very first tutorial this week. And to be honest, I had a little bit of a panic because it was that much of a good question that I was just like a bit baffled for a second. And I've looked it up. And what you need to do is you need to take the row that you've got, the closest row that you've got that's less than the row that you're looking for. So in this case, if you've got rows for 20 degrees of freedom, 24 degrees of freedom, you're looking for 22 degrees of freedom, use the row for the 20 degrees of freedom. Just stick that value in, and that's as good as you're going to get in the circumstances. So that's how to approach that. The value in this case for T 0.975 is 2.074. And then plugging that in along with all of the other values in the question, overall you should get that your 95% confidence interval is minus 3.98 up to 9.78. Now in this case, 0 is in that range. So it's plausible, it's possible that sample A and sample B come from the same data with the same underlying distribution. So this interval's got 0 in it, which implies we can't rule out we can't rule out the possibility that the two means are the same, so mu A equals mu B, which is a different conclusion than we reached in question 2. All right, so we've got 10 minutes left to take a look at question 5. Now, question 5 is a bit different because the data that we've been given comes from a different distribution. So what in each area, we've got a certain number of registered voters. Okay, and we've got a certain number of active voters, so people who actually vote.
So in the first area, we've got 288 registered voters that we survey. We observe that 141 of them actually go to the polls to vote. So we've got an estimate for the proportion of voters who are active. Which is going to be 141 divided by 288. Now, if we have a think about this, we're thinking, well, people are either active voters or they're not. So for everybody in this sample of 288 people, when I ask them, do you vote or did you vote or did you not vote? They either say yes or no. So the number of active voters is going to be binomially distributed. X equal the number of active voters. Okay. And X is going to be binomially distributed. I'm asking 288 people. I don't know what proportion of them say yes, so I don't know which proportion of them are actually active. So I'm looking for that P1. What is the value of P1? And the best guess I've got as to what P1 is 141 divided by 288. So the proportion that I've actually observed when I sampled people. The same is going to apply for the second area as well. So in the second area, I've got 216 people who answered my survey. And of those people, 125 actually went out to vote. So the best guess I've got of the proportion of active voters is 125 divided by 216. So I'm in this situation, and what the question is asking me for is for a confidence interval for the difference between P1 and P2. Now, I've got to use the information that I've got, so I'm guessing that these P hats have got to go in there somewhere because that's the only information that I've got. Now, the other thing that needs to go into the formula for the confidence interval is going to be the standard error of the PIs. So, the standard error of the PIs is going to have the form PI times 1 minus PI. I think it's covered in question 1, and that's to do with what the variance of the binomial distribution looks like. So with this in mind, have a think about what you're going to do with a 95% confidence interval for the difference between P1 and P2. I think one thing we can say for sure is that we're going to want to center this on the difference between the ratios we've observed in our samples. So the first term we're going to want here is P1 hat minus P2 hat, because that's our best guess at what that difference is from the data that we've got. And then I'm going to want a plus and minus. Now, we've discussed that the underlying data is definitely binomially distributed, so it's not normally distributed. I can use Z here. I can use Z 0.975, which has cropped up so many times in this question, in this exercise sheet so far, that I know that it's 1.96 by this point. And then I'm going to have something in a large square root that I need to take the square root of. And the question is, what exactly is it that needs to go in here? What is it that needs to go in here? So that's what I'm going to leave you with for the last few minutes is, what do you think needs to go in here? I've given you a little bit of a hint here as to something that you might want to use. So have a think about what you would like to put in here. Use the values that you've been given in the question that I've just written out for you there to plug in to give the endpoints of the 95% confidence interval. Give it a go. See what conclusion you'd like to draw. Would you like to say, yes, I think P1 is equal to P2? No, I don't think I want to be saying that. I think P1 is not equal to P2. If you get to the point where you've got an opinion, so you found a confidence interval and you're like, yes, I want to say, yeah, I think P1 is equal to P2. Post it in the chat and we can see how many people go either way on that. But if you don't feel confident, that's also absolutely fine. So I'm going to stop rambling and I'm going to give you until the end of the lesson, which is about 4 minutes, just to try and calculate there. Post in the chat if you need anything, then we're going to come back right at the very, very end for 10 to 15 seconds just to give you the final answer as a little bit of a motivator or a check as to what you're doing. So I've written a little hint out there for you as to what formula to use. You hadn't got that far yet. Okay, so let's come back and finish this off before my family start disturbing us again. So the two numbers are minus 0.177 and minus 0.0015. So we're pretty close to being able to conclude that P1 equals P2, but 0 is not actually in this range. So 0 is not in this interval. So we can't conclude to P2 from the data that we've got. We're not 100% sure. Well, we are, yeah, it looks like a close thing because that second number is very, very close to 0, really. But with the data that we've got, we can't conclude P1 is equal to P2. What we might want to be doing is, seeing as it's so close, is maybe doing some more observations and seeing if that sort of changes it to more ambiguous or less ambiguous. Seems like somebody's telling us what she thinks about life in general again, which is great. Anyway, so yeah, so in this case, we can't conclude that the proportion of the voters that are registered who actually vote is the same in the two states. This is something that we're not allowed to conclude from the data that we've been given. I hope you all got there in the amount of time given, but I realise it was a bit tight and it didn't really give you that amount of time to calculate, especially if you had to look up what was going on here. Okay, so with that in mind, we've gone 1 minute over, but we were really close to being on time and finishing question 5, which I was quite impressed by, actually. So if you want to hang around and ask anything, I'm going to still be here for a little bit. I'm sure Sarah Lees is going to come back. If not, I will see you next week for week number 11. Looking at the exercise sheets, we actually have an exercise sheet for week 11 and week 12. So twice more, and then we're nearly there. See you next week. Bye-bye. Okay, see you next week, guys. I'm going to leave you with Sarah Lee's office chair. Bye-bye.